Hello, 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 hello. Okay, that is hello, hello, hello. All right, hello, and hello. All right, good afternoon. Okay, hello, Lila. Hello, Mike. Hello, Raymond. Hello, Tania. Hello, hello. Sorry. Hello, Louis. Good afternoon, Luis. Hello, Jadith. Hello, Sophia. Good afternoon, Leah. Hey. I'm doing it again. I knew it right at the beginning. Can you please correct me? I did it right at the beginning of the semester, didn't I? Thank you. Good afternoon, Leah. Leah. Wait, tell me, Leah. Wait, and good afternoon, Samaya. And good afternoon. I know it's so late in the semester, but I don't want to get good. And hello, Shen. Wait, I'm so sorry. Leah. It's Leah, not Leia, correct?
Yeah, it's Leah.
Okay. Just making sure. Okay, sorry. I know it's really late. I just want okay. All right, so hello. Wait, more people coming in. Wait, and I see there's something in the direct chat. Hold on one sec. But wait. So good afternoon, Leah. And good afternoon, Samaya. Good afternoon, Camille. Hello, Shen. Hello, Nico. Oh, and hello, Mancha. Ooh. I'm seeing some fascinating avatars. Okay. Good, thank you. I mean, it's a little rocky, right? And thank you, Mantra, for asking. Getting a little harder to admit, but all good. I'm very lucky, very blessed. A little harder, thank you. But and some of it is affecting you guys, which is what I don't want. But anyway, but thank you. Hope you all are doing well. I know it's a tough time of the year for everybody. We're almost there. So wait. So there's something in the direct chat. We're gonna get back to physics in a moment. There's something in the direct chat. I'm not going to read the person's name, obviously, but totally missed the last homework due to human error. Can you hand it in late? Yes, absolutely. Everybody, like compassion goes both ways, or the request for compassion goes both ways. Absolutely. We're at the stage now in the semester. That's what you want to be doing is finding anything that you haven't turned in or that you need to do revisions on, or the most recent homework which we're talking about right now in class anyway. You absolutely could still turn in. Yes. I mean, if you didn't turn in a draft when it was due, you might not get all of the points, but you're going to get a lot of points, and it's totally worth it. Um, this most recent homework, okay, and it's very hard, but it'll get easier because of the things I'm talking about in class now, like today. Um, so if you turned in anything on it and you really struggled, you could revise and get all the points. If you didn't turn anything at all, you could still get most of the points. That's definitely true with that homework and others. But bottom line, what you would want to be focusing on now in the material, if anything, is the most recent, is this material of the homework called Gauss's law, which is about electrostatic flux. Like that is like our like kind of our last big topic of the year of the semester. That's what I'm trying to clarify in class. So, and that's what would be on. I mean, that's a big part of the final exam, which there's clarification and announcement posted in Google Classroom. So yeah, if you're going to focus on anything, it's definitely not too late to focus on that. All right, but I think that's clear. So let me go back. I just lost the chat. Sorry, what happened? Oh, I see. Hold on one second. So I want to get back to that. To what? Oh, okay. Yeah, no problem. Direct hyper. No, I appreciate it. You guys are being very patient with me as well. Okay, and more people are coming in. So I want to get to physics here. Uh, Yeah, I keep sort of writing very similar equations on the front board and like sort of getting to them, but sort of not. So I really want to, particularly that top one. So that's what I want to get back to now, where we were on Monday, because I think that constitutes all the announcements. Yeah. So, okay. So I'm focusing now. I'm trying to build up to or focus on the top equation on the board right now. So let me back up and remind you of where we were just at the end of Monday. All right, sorry. Okay. So what I just drew, this is again a little bit of backup, a little bit of like review or summarize where we ended on Monday. What I'm saying, well, in English, what I am saying is a little bit of flux, a little bit of electrostatic flux is defined to be electric field flowing through a little bit of area. Flux, E flux, electrostatic flux means E field through area. I'm going to say that one more different way. In English, in the simplest possible case, flux is the product of field strength times area. So, in the simplest possible case, when we're talking about flux, we're through some space, we talk about looking at a two-dimensional region of space. We look at a slice of space, like a square or a rectangle or a flat disk or whatever. We look at some flat cross section of space. We ask, how strong is the field going through that region of space? So, put more specifically, we ask, how dense are the field lines going through that region of space? We take the density of field lines, the strength of the field, measured in newtons per coulomb, and we multiply by the area of the space measured in square meters. We multiply newtons per coulomb of field times square meters of space, and we get what is called electrostatic flux. So again, this is English now. This is like the big intuitive picture. When you're measuring flux, you're measuring how strong is the field through some area, like literally area, like two-dimensional region of space. When you ask how big is the flux, you're asking how much field is there in that area, and the bigger the field strength, the bigger the flux, and or the bigger the area, the bigger the flux. So it's like multiplication, not division. If either number is zero, then the whole thing is zero. Okay. So that's in general what flux is. But that, excuse me, that that is what flux is in what I'm calling a little case, in a case that is so small that the numbers are really easy to work with. Okay, so the rest of what I have to say is like the nuances of generalizing that idea to more possible cases. So first have it in your mind. I'm just gonna say it one more time. What flux is field through area, right? But then nuance number one, that I was spending all the time on Monday dealing with. So I'm just going to capture, summarize now. Excuse me, sorry, I'm changing the view of the screen. Nuance number one is when I say field going through an area, I really do mean field going through the area. In fact, in Latin, flux means flow, not flow through time, flow through space in this context. So when we count, when we look at the field strength hitting some area, i.e., when we count up the number of field lines per unit area going through that area, actually, we only want to look at the components of the field lines that are actually busting through the area, i.e., making right angles with the area, right? This is where this also all the business about cosine or the dot product that we spoke about Monday. That's where that all comes into play. Is that actually, if any field lines are going parallel to the area, we don't want to count them at all. They're not flowing through the area, then they're just grazing the area. And furthermore, then, if any field lines are coming in at some arbitrary angle, theta, we only want to count the components of those field lines that are perpendicular to the area. So, in order to do this, in order to just count certain components, we do a dot product. A dot product between two vectors is the product of two vectors that is itself a scalar, right? And arises by only measuring components that are lined up with each other. Now, so strictly speaking, when you're talking about a little bit of flux over a little bit of area, flux is really the dot product of the E field vector with the area vector. However, okay, so it's a dot product. And it's a dot with so all, even if you don't like all my vector notation or you're like the end and the cosine, what that's all just trying to say is where flux is stuff that's actually going through the area perpendicular to it. Okay. But now, last subtlety of that, or like last detail of that before we're going, it is a little confusing because what I want you to know in general, especially if you're going on in STEM or you're ever going to do physics or math in any way again, you need to know that in general, the dot product measures how parallel two vectors are, and on purpose. It measures the extent to which two vectors are aligned, and therefore treats them as two numbers on the same number line and spits out a purely numerical answer, a scalar product. That's what the dot product does. Yet I keep saying that with flux, we're looking at the extent to which the E field is perpendicular to the area. That's confusing. I want to remind you one more time. It really sounds like I'm contradicting myself. If you're at all confused by that, if you're like, wait, is he saying parallel or perpendicular? Then you are with me. I'm not making a mistake and I'm not trying to confuse you. But there is a very tricky issue here. So let's hear it one more time. The dot product measures how parallel two vectors are. That's math. We here are trying to look at how perpendicular an E field vector is with an area. An area itself is not a vector. An area is just like a square, or like, right? An area is just a size, 5 square centimeters or 5 square inches or whatever, right? So an area is not a vector. But we care about the orientation of like the area is two-dimensional, not an arrow. But we're here focused on the orientation of the area relative to the E field vector. So the way we do that, the way we can use math in order to physically measure and account for the angle between the E field vector and the area itself is what we do is we attach a vector to the area. And we attach that vector like right to the center of the area. We put a little arrow there, like a flag in our minds, sticking out from the area. And the length of that flag, that arrow, it represents the size of the area. And the orientation of that arrow represents or the direction of that arrow represents the orientation of the area. So if the area twists by an angle theta, the arrow sticking out of it in our minds will twist by an angle theta. So we have this little flag or this little vector in our minds stuck to the area. And from here on in, that arrow, that vector represents the size and direction of the area itself. Okay. So we're turning area into a vector quantity by attaching an arrow to it. The catch, though, is that the simplest way to attach this arrow is to attach it perpendicular to the area. The arrow, that's why I call the arrow an N arrow for normal. The area vector is by design, by convention, normal, perpendicular to the area itself. Therefore, if an E field vector is purely perpendicular to an area, then it will, in real life, in space, then the E field vector will be purely parallel to the norm vector that represents that area. So basically, so you always have to adjust by 90 degrees in your mind, or you just have to hear the adjustment once in your mind. So in the long run, what I'm saying is, and stop, I'm going to go on and say, sorry, I'm going to. I'm going to go on in a second if you tell me to, or I'm not, if you tell me not to. But the summary I'm trying to say is mathematically, flux over a little bit of area is the dot product between the E field vector and the area vector. Mathematically, that means we're measuring how parallel the E field vector is with the area vector. But physically, what that really means, since the area vector sticks out perpendicularly to the area itself, physically, when we measure the dot product between E and delta S, what we're physically really doing is measuring how much the E field is perpendicular to the area. Bottom line, to measure flux is to measure how many E field lines are flowing through an area perpendicular to that area. I'm going to pause for one second. So just please raise your hand if I should move on, or put in the direct chat that I shouldn't. Oh, yes. Okay, Nico, that works for me. Absolutely. And Layla, yes, let's move on. Great. Thank you. Okay. Okay. And you should definitely submit that for points, you two, for please move forward. Okay. Okay. Okay, thank you. Okay, so that was that issue. That's the issue of the directions and the vectors and all that. But now there's one last issue I have to deal with. Like I keep saying a little bit of flux is E field through a little bit of area. I keep saying little, little. Why do I keep saying little? Like, what does that even mean? How little is little? What I mean when I say little or small is I mean an area that is small enough to prevent any variation in the vector E. Like up until now, everything I've said, in other words, is picturing an area that is small enough that we have one value for E field to work with, that the E field lines through the area, the pattern of the E field lines isn't changing throughout that area. If the area is small enough that we've looked at, we could probably rely on that. But once the area gets big enough, the E field lines might be changing in their pattern, or the E field vectors may be changing in their size and orientation, right? So the question is, how do we deal with areas that are large enough to allow for, right? The question is, how do we deal with areas that are big enough to allow for continuous variation in the magnitude and direction of E? Well, the bottom line answer is that the whole is equal to the sum of its parts. In other words, in other words, say we have this big area and the E field lines are doing one thing over here and another thing over here and another thing over here. So let me be more specific. Let's say in the first square centimeter, the E field strength is 10 newtons per coulomb. And then in the next square centimeter, the E field strength is 20 newtons per coulomb. And then in the next square centimeter, the E field strength is 30 newtons per coulomb, etc. Well, in a case like that, because we believe that forces and fields obey superposition, because we believe that the whole is equal to the sum of its independent parts, what we could say is, oh, no problem. We'll just take this big area and divide it into small equal areas, each of which is equal in size to the next, but small enough to just capture one number for field. So we'll say the total flux is the 10 newtons per coulomb times this 1 square centimeter plus 20 newtons per coulomb times this 1 square centimeter plus 30 newtons per coulomb times this 1 square centimeter, et cetera, and just add them all up, right? And that would work. That does work. In the case, Okay. What I'm saying here is in the case that I just described, if you had a situation where you could divide your big area down into small and small chunks, each of which did have its own E value, E number, then you would just say the whole is equal to the sum of its parts. And you would capture that mathematically with the summing sigma notation, right? Sigma, that big capital letter sigma, is what we use whenever we're doing a discrete sum in math, right? And discrete means distinguishable, separatable, countable, right? Choppable into chunks. That's what discrete means in math, as opposed to continuous, right? So, how does you remember how that sigma notation works? It's the sigma notation is really a procedure being encoded. It's saying, look, here's what you do. You set an index, started at one, and you're going to ultimately let this index run all the way from the value one all the way to your highest possible value, which we'll call n, right? Um, So it's saying like, okay, set your index to one and now go. Perform this procedure. First, go to the 1th bit of area, delta S sub one. Go to the first square centimeter. Ask what the E field strength is at, or the E field vector is at that area. Ask what the first, the E sub one, the first E field value that corresponds to that area, take the two, multiply them together, or in this case, do a dot product together, take the answer, throw it into your bag. So do like 1 square centimeter times 10 newtons per coulomb, get that product, throw it in your bag. Okay, then raise the index to 2. Go to the second square centimeter, multiply it by the corresponding second E field vector, multiply the two together, throw it into your bag, your mental bag. Keep going, keep going, keep going until you get to the very final. Wait, oh, very good. Okay, okay. That's where very good, Nico. That is where I'm going. I haven't said it yet, but that's totally where I'm going with this. Yes, and I'm about to go. That's awesome. You should totally. I'll also take that as a hint that I should move faster, but you should totally submit that for points. That's awesome. So I'm saying right now to everybody that sigma is the sigma, the Greek letter sigma, stands for sum. It's like an S, right? It stands for sum. It's what we use for sums, but we use it in the case where the sum is discrete, where you literally can go product number one, product number two, product number three, product number last, and add them all up, and the result is your discrete sum. That's what we could do to calculate flux if we had a situation where we could break down the area into small enough sizes such that each one of the small sizes had its own value for E. But here's where Nico is going and where I'm going. The fact of the matter is, in life, that is not generally what happens. Generally speaking, you're going to have an area where if the E field is changing at all through that area, it doesn't change in cartoon steps. It changes smoothly, continuously, right? What does continuous mean? Continuous means infinitely divisible. It means that no matter whether you're looking at square centimeter or square millimeter or down to square angstrom, you can't get small enough to capture a region with a constant E field. Continuous change. If the E field is a so if the E field is a continuous, if the E field varies as a continuous function of area, that means there is no finite amount of area you could pick small enough to prevent change. It's changing down at the infinitely divisible level, right? So in that case, what we do, In the continuous case, we want to take the sum to the limit. And what Nico, right? That's what we want to do. I'm not saying I know how to do that yet, but I'm just saying that's what we want. We want the sum of all of the products of E field times area in the limiting case where each area is as small as possible, as close as it can be to zero without actually being zero, right? Well, what Nico is correctly anticipating is we have a word for that. We have a concept for that. It's called the integral. What I'm saying, now again, there's a couple of subtleties here. But what I'm saying, first of all, I mean, I know you've seen a million integrals in math, but if you're like me, maybe you've done a million integrals, maybe you even got an A in the class and know how to do them, but maybe you never quite understood what they actually meant or why they ever come up or how to set them up or when to set them up, like in a physics class. Here's how, where, when, why. Again, this is Nico's point. The integral, by definition, is just the sum of a bunch of products taken to the limit. The integral is the sum, but in the continuous case. Literally, if you walk up to me on the street and just say, "What is an integral?" You might think I'd say the antiderivative or something, but I wouldn't. I mean, don't get me started. That is a double equal sign. That is not a triple equal sign. If you ask me what is an integral, I would say to you an integral is a continuous sum of products. The integral is what happens when we take sum to the limit as the independent variable step size goes to zero. Specifically, and note the notation is not a coincidence. Sigma means S for sum. The sigma is jagged and pointed and clunky. We use that when we're doing sums in a jagged, pointed, clunky case of chop, 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 chop. When we smooth out the sum, when we look down at such a fine grained level that each little sliver of what we're adding up is infinitely small so that all the slivers are attached to one another and the sum is smooth and continuous, then we take that jagged sigma that was supposed to stand for S for sum and we swap it out and we swap in a smooth S for integral. Did I know that the integral sign was actually supposed to be an S? No, I did not. So until I did. So if you never noticed that before, notice it now. It actually makes a lot of sense. The integral sign is an S. It's a smooth S because we just smoothed out the sum. The sum of what? The sum of a bunch of products. Products of what? Of the independent variable with the dependent variable of some function. That's why the delta S in our sum changed into a ds in the integral, or a d whatever, in whatever integral you're talking about. Why there's always a d something in the integral is not just to give you a headache as a math student. It's for a reason. It's because the integral is a sum of a bunch of dependent variable values multiplied by a bunch of independent variable values. It's the sum of a bunch of products between dependent variable and independent variable. When we go from discrete to continuous, we change the delta to a d and we change the sigma to an s. That's what an integral is. It's a continuous sum of products. We use it, we need it when the dependent variable is literally a variable where it's varying smoothly and continuously throughout the domain of the independent variable. This is true of integrals in general. I never understood this until I did. Like honestly, I did a bunch of integrals like you, but I never knew why, and I certainly couldn't set them up. I just did them. And then when I got to physics and they were like asking me to set them up or picture it, I had no idea what they were talking about until I did. What I'm saying, I'm going to say one more time and then I'm going to move on. Yes, I'm going to say one more time what I'm saying. Well, I'm saying this. I'm saying this. Hold on. So here's the math point I'm making. Ay, yay. Why? Oh my God. Sorry. Excuse me. Trying to say, like for a moment, forget the fundamental theorem in calculus or anything. Oh, thank you. Sorry. Oh, wait. Wait. I'll move forward. I'm sorry. Wait. Yeah, wait. Wait. Okay, wait. Actually, there's like mixed messages in the chat. So someone in the chat is asking me to move forward, and definitely you should submit for points for that, for saying that, and I will. Thank you. But then actually, since there's other things, I will move forward in a second. But yes, I think this is a very important math point, and this is not. And look, I won't get bogged down, but I just know some of us understand the physics better if we have the calculus first, but some of us understand the calculus better if we see the physics first. Okay, it's not a matter of math teachers versus physics teachers or anything like that, but yes, it does help me to be clear on this. So what I just want to say before I move, but thank you. I mean, I appreciate that. So and I'm glad that means you're understanding what I'm saying. But I also appreciate someone saying in the chat to move forward. So, okay. So wait, math wise, I'm saying in general, what the integral is that, which means, again, like you always did in math, maybe it'll even make more sense now. Since math doesn't care what the variables are, like they're just y and x, right? So in math, what you're supposed to picture whenever you do an integral, you're supposed to picture yourself walking along the x-axis, taking steps along the x-axis, and at every step you take, looking up and asking, what's the value of the dependent variable right here where I'm standing, right? For whatever x I'm standing at, what's the value of y? So you take a step along the x-axis, you look up to see the y value, and you multiply the two together, and you throw it in your bag, and then you take the next step. When you multiply those two values together, that's in math where they picture the height of a rectangle times the width of a rectangle, right? This is why they say in math the area under the curve. They're imagining you taking steps along the x-axis, and at every step you take, asking what's the value of the dependent variable. You multiply the two together, so you get the area of that little rectangle, and then you take the next step and you add up all the rectangles together, and the whole total area that you've gotten is the value of the integral throughout that space. The catch is that every one of the steps you take is infinitesimal, it's infinitely small, so that you're grabbing all of the possible variation of these rectangle heights, right? Now, again, the person that asked me to move on, I'm glad you get it. Bear with me for a second, but I think so. That's in math, right? In general, what the integral is the continuous sum of these products, always. So why does the integral ever come up? What are you using it for? You're always looking at the integral to find out what is the effect of the dependent variable throughout some interval of the independent variable. Let me make that more concrete now by going back to the physics. So now moving on. Here in this physics, there's more subtleties involved here. Here in this physics, if you understood that concept, now I'm saying, so that's just like how we get to integrals in the first place. So circling back, I'm agreeing with Nico and other people that yes, I'm ultimately going to say that what flux is, well, I'll write it again. I'm saying then that flux itself in the general case, if you want to capture all the nuances and possibilities of flux, a little bit of flux is field dot product area. But I'm sorry, I can't. A little bit of flux is field times area, dot product with area. But if if the area is really big, what we have to do is the integral of field with respect to area. We have So nuance number one is we're now dealing with a dot product. That's specific to this physics. Not all integrals. Integrals are not always dot products, but they are always products. And now we're saying that since we're in physics, this particular kind of integral involves a particular kind of product known as a dot product. Okay, that was the subtlety of Monday. Now, also, I'm saying this particular integral that we're looking at here happens to be two-dimensional. Okay, so we're taking the concept and we're sort of doing it twice. I mean, we are doing it twice. We're saying now that physically what we're doing is we're not just stepping along any arbitrary abstract x-axis on a graph. We're taking steps along an area of space. We're literally taking us, so we're taking one two-dimensional step at a time. So that's why my variable here, my independent variable, is not dx or dy, it's ds, technically speaking, if you like, ds is really like dx times dy. I mean, it is. Okay. So what we're doing really is one integral times what we're really doing. Okay, two options, whichever one works better for you. They're both the same. The way I'm describing it and the way I'll continue to sort of talk about it is I picture myself in some area taking one square centimeter step at a time. And at each square centimeter I step, I ask, what's the value of the E field here? Well, what's the vector E field here? How many field lines in what direction are they hitting at this square centimeter? Whatever the answer in newtons per coulomb is that I get, I multiply by that square centimeter, I throw it in my bag, and I walk to the next square centimeter, and I keep going. Only these square centimeters are infinitesimally small squares, right? That's one way of thinking about it. So each infinitesimal is really a tile rather than a step. It's two-dimensional. The other would be, but if you don't like, and that's why it's called ds, S for surface. If you don't like that, the other way you could think about it is that I'm walking, I have some big area, and I just take steps all the way along the length. Each time I take a step along the length, I ask what the E field is there, multiply the two together, throw it in my bag, keep going, keep going, keep going. And then after I finish the whole length, I walk along the width, right? So if you think about it that way, that's why it's a double integral sign. Okay, it's a double integral sign because the variable of integration is really two-dimensional. Whether you want to think of it as one integral times another or a sort of simultaneous package of two integrals, either way is fine. The point is, so well, I'm going to go on. I promise I'm going to go on, sort of. What I'm trying to say for the moment is the integral in general is the continuous sum. The specific type of integral we're doing here is a two-dimensional integral of dot products. Okay, so that's a mouth. So not all integrals are two-dimensional and not all integrals involve dot products. But this one, the flux one, does. Is. Okay, so sort of in quasi-mathy English, like the conclusion of what I'm saying is that what flux is stuff through area. But in order to capture all the possible cases and all the nuances, flux is the continuous sum of a bunch of dot products between E field vector and area vector. That's what flux is. Okay. That's a lot, maybe, or maybe not. I'm going to say a little bit more. Okay, that's the mathy way of looking at it. It's the double integral of the dot product of the field vector with the area vector. That's what flux is. Now, does it, what does that mean in English? Or why is it useful? Well, why is it useful? Also, I'll quickly say, well, it's similar, it's useful in a way that's similar to why when you first define work in physics, like in physics 203 or whatever, work is the integral of force times displacement, right? When you define work, you're looking at the accumulated effect of force throughout some one-dimensional space. Well, whenever you do an integral, you're looking at the accumulated effect of the dependent variable throughout the region defined by the independent variable. So similarly here, when we look at flux, we're looking at what is the E field doing to a certain amount of space. Instead of just looking at the E field at a point, we're looking at the effect, the consequence, the impact of the E field throughout some finite region of space. Uh, okay. Okay. So what flux is, and I'm almost done about this. What flux is what I just wrote here. It's the accumulated effect of field throughout some finite region of two-dimensional space or some finite two-dimensional region of space. And remember, field is force waiting to happen. So, so when you calculate flux, you're asking how much force is waiting to happen to act on possible test charges throughout a certain area of space. Okay. Right. So in English again, flux is field strength times area, as long as by strength you mean strength of the field lines that are perpendicular to that area, right? So now wait a minute. If we're talking about field lines, remember, here's the key, and we are almost done, I promise. But here's the key. When you're talking, like, if you're talking about field vectors, then the length of the vector indicates the strength of the field. But if we're talking about field lines, as we started to 2 weeks ago or three, if you're talking about lines, remember with lines, with field lines, they don't have length. They're not arrows. They're wavy, curvy, bendy. With lines, It's the density of the lines in a picture that the density of lines per unit area that indicates field strength, right? So with lines, flux equals number, field strength is captured by number of lines per area. But then we're multiplying that by area, right? So wait, this is really weird. For all of this abstract math that I'm saying, I'm saying the flux through some area is the field strength times that area. But if you're drawing pictures with field lines, field strength is represented by the number of field lines per given area. So according to this, flux is number of field lines per area times area. So actually, if you really want to picture what I'm talking about in straightforward terms, in the end of the day, and please, even if I lost you or we are just about done with this content. Please hear me out on this. After all of this complicated math, and it's not to waste your time, it's very real stuff. But after all this complicated mathematical way of saying it, if through all that you're like, I get it, but why do I care? I get it, but why do I care? The reason we care about flux really is that flux means number of lines per area times area. Number of lines per area times area. The areas cancel out. What flux really means is number of lines. What I'm really saying is, and this gets to your homework, that which you could still do. Say someone asks, and I'm going to do this really quickly. I see it at 4 o'clock. Say someone gives you a point charge, a point source, positive Q, and asks you, for example, like in the homework, and asks you to calculate the flux through a sphere surrounding the point charge, through the surface of a sphere surrounding it. It all sounds very abstract, right? What they're really they're asking what's the total amount of field busting through the surface of that sphere. But what they're really asking then, in the end of the day, they're saying, picture the field line diagram. Here. They're saying, picture the field line diagram. Field lines go on forever, right? They're saying, if they ask what's the flux going through the surface of that sphere, well, the flux is number of lines per area times the area of that sphere. In other words, the number of lines going through that sphere. The flux through the surface of sphere in this case would just be 8 lines. Whatever. And if you've picked the scaling factor properly to make your field line representation, as was discussed in the videos, then you could convert that 8 lines into an actual number of newtons per coulomb times meters per square. What I'm saying is this very quickly, it's 402. I'm saying the big conclusion I'm coming to here is the flux through that sphere is just the number of lines going through the sphere. And once you think of flux as number of lines, you immediately see that no matter how big I can make that sphere really big or really small, I can make that sphere a square, and the number of lines isn't going to change. The number of lines going through that closed surface will be the same no matter what the shape of that closed surface is. If you really understand that flux is really just a way of saying count the number of field lines. Electrostatic flux is number of field lines. The I'm saying the only, well, I'll just read it very quickly. Gauss's law. This is put in English. I'll put it mathematically, and that'll be it. The number of field lines through any closed surface depends only on the amount of charge enclosed by that surface. The only way that field lines can start is at a positive charge, right? So the only reason field lines ever start is positive charge. And once they start, they don't end unless they hit a negative charge. So if you want to know how many field lines are coming out of some closed surface, you just have to look at how much charge is inside that closed surface. You could change the size or the shape of the surface or the shape of the enclosed charge, and you're going to get the same number of field lines no matter what. Therefore, you're going to get the same flux no matter what. In other words, Gauss's law in math is the flux through any closed surface is fully determined by the charge enclosed by that surface over a constant. We'll talk more about that next week, but that's the law. And I'm stopping that, but it just means you can't, once you're counting field lines, you can't change the count by changing the shape that's enclosing them. So I'm going to stop because of this, because I was already, I don't, we have limited, we have 15 minutes. What I'd like you to do right now, if you have already gotten points, 20 points for doing a teacher evaluation, then please go and Quark bless you and thank you for your patience. But if you have not, I want, please stay with me. I'll shut up. I'll put the link in the chat. Please do the teacher evaluation, the professor evaluation. I won't see it, but I'll see the aggregate data and I care. We all care. So technically, you have me twice, once for lecture and once for recitation. I do it the same way. You can evaluate me twice the same way, whatever. But the link, but once you put once you screenshot completion of 2 evaluations, you get 20 points, and I'll do the points right now. Once you have the points, leave, or if you already have the points, leave. But if not, please do. So the link is right there. Please do 2 evaluations. And yeah, just please do them and you'll get the points. And I'm doing the points right now. And then what? Okay, I see. Right. And just submit the evidence that you've done them. And then thank you very much. Yes, I see. Perfect. Okay, thank you. And so thank you for your patience and all of that. And once you see the points, then go.
Professor, I just wanted to say it says that you need a John Jay username, so
You're an e-permit student? I'm sorry. Okay, wait.
yeah.
Yeah, okay. So that is a real problem at John Jay. You're right. Wait. Yeah, yeah. Oh my God, I have a lot of e-permits to discuss. Oh yeah, yeah. So right, and if you did it right before class, or if you did it at all, then you got the points and then you can go. Now, if you're, oh my God, there's a lot of you. So here's the sad thing. If you're an e-permit student, apparently you can't do it, which is terrible. And I'm trying to get that changed. I don't, so you apparently you can't do it, and I don't understand, but you can still get the points for me. So hang out for a second. If you're an e-permit student, just in the portal, in the Google Classroom portal, just write a note to say I'm an e-permit student and I'll give you and just wait till I'll give you the points and then go. Okay. Yeah, if you're a student from a different college, it's so lame. I don't know why this is. And I'm on the committee, so I need to get this. But yeah, points for wishful. Right, right. So yeah, just hang out for a second. If you're an e-permit student, just write in the portal, I'm an e-permit student, and I'll give you the points because it's not your uh and once you see the points, either way, have a nice day and thank you for your patience. Oh, and I'm stopping the recording. I'm sorry. The